Everyone, thanks for joining the user group. Today I'm going to give a status update of DAOS core features. And yeah, here is the agenda. First of all, we will spend a little bit of time to introduce data protection and self-healing from high level to give everyone some background. Then I will introduce a few main features developed in this year. The first one is end-to-end data integrity support by using checksum. Then I'll introduce all the data reconstruction operations supported by DAOS and a little bit more details about the main one added this year, online server edition. After that, I'll present our Erasure coding protocol and the preview version of the EC will be available in the next release. And the last main feature is distributed transaction of DAOS. Okay, so DAOS can be deployed on storage cluster with thousands of storage nodes and tens of thousands of storage devices. So node or device failure is not a rare event in a large deployment, and DAOS should be able to prevent data loss by software data protection and respond to I/O request instead of blocking when failure happens. So DAOS provides both replication and erasure coding for data protection and recovery. Both of them can protect user data by making use of data redundancy, and the eventual goal of having data protection is system resilience. So user data can be recovered to the same redundancy level and tolerate the same number of failures. And the module that is responsible for data recovery is called self-healing system in DAOS. And the self-healing system of DAOS includes two components. The first component is health monitoring protocol, SWIM. It's a gossip-based protocol and can detect node failure in a certain time. So DAOS relies on this protocol to detect node failure. The second component is data recovery system, and Rebuild is the protocol for coordinating data recovery. The main reason that I went through the self-healing system and the Rebuild protocol is because all the features I'm going to present today are about data integrity and data availability. Checksum is the first feature we developed for these goals. And in the DAOS I/O stack, whenever application writes something to DAOS system, the DAOS client stack can compute checksum for application data and send the checksum to the server side. When the DAOS server receives the data and its checksum, it can store both data and checksum in the backend storage, which is persistent memory and NVMe SSD. If the application wants to read back the data, then DAOS server will return checksum and data back to DAOS client. So DAOS client can verify the checksum and see if data is still correct. If it is, then DAOS client will notify the application completion of the I/O. But if it is not correct, then the DAOS client will retry and will try to get the correct data if there is data protection. So it can either read from another replica or reconstruct data for EC protected data. And this is called the degraded mode I/O. The degraded I/O is transparent to application. So it means that application won't see any error, but it might see performance degradation, especially for erasure coding, right? Because and we will explain it later. So checksum is already in the upstream, and it will be available in the next release, and in the future, we will support checksum scrubbing. It means that even nobody is reading data, there is a background service which can continuously scan all the data and verify checksum of them. If there is corrupted data, then the service will run data recovery protocol to reconstruct corrupted data. Actually, the data reconstruction and the recovery protocol can be applied to a few different use cases. The first one is rebuild, and as I have already introduced, it's mainly for data recovery after storage node or storage device failure. And the second one is drain. It means user can manually evict or exclude storage nodes or storage device from the pool. And so for maintenance or replacement or whatever reason, and it's quite similar. It's quite similar as rebuild. Data on the node being evicted should be reconstructed in somewhere else before admin can shut down the server, so we can support the same level of data protection after eviction. The third one is reintegration. It's really about how to bring back a node after either manually or automated eviction. And the last use case is server addition, so user can add more storage to the pool. In this case, DAOS server can automatically rebalance data and migrate part of the whole data set to those newly added storage. So user can get an even amount of free space everywhere and higher aggregated I/O performance from the storage pool. This page is a short description about the internal protocol of online server addition. It is actually a unified protocol for all the data for all the data migration use cases, including rebuild, drain, reintegration, and rebalancing. Briefly, all the storage targets should scan as their local object store and run placement algorithm against those objects and find out all the objects impacted by the pool membership change. I mean, because we are adding more storage nodes to the pool, right? Then they should send the impacted object IDs to new targets, and those new targets will drive the data migration process by pooling data. So that's a short description about the online server addition. Okay, the second feature and the most important and the most important feature we developed in this year is erasure coding. Actually, in the first version of DAOS, we already have preview version of replication, and the process of replication is simplicity, right? We just send I/O request to all replicas on write and send I/O request to one replica on read. And when failure happens, replication has minimum performance impact on application. This is because application can only needs to send I/O to a different replica for the read. However, major issue of replication is the write bandwidth consumption is high and the capacity overhead is high as well. This is because the nature of replication, right? If number of replica is n, then we have to write n times the actual data set size. Erasure coding can significantly reduce the bandwidth and the capacity overhead. But EC needs to consume compute resource on both client and server, and it has way more complex and expensive data recovery protocol on failure. So that's the reason we want to support both of them. The major functionalities of DAOS EC include a few areas. So first of all, it's an implementation of a resettlement-based EC and the data recovery based on EC. It includes two parts. The first part is the client side should be able to do data reconstruction in flight. Or let's say if an object lost a data shard due to a node or device failure, how does this server to serve the read based on surviving data shards and the parities? And the second part is rebuild. It should be able to recover data redundancy by of EC object in the background. We have this protocol for replicated object, but it needs to make some change to make it support rebuild for EC object. Then we should have a background service which can do background encoding and space reclaiming. This is really just what we call aggregation, but we should extend the functionality of the aggregation to support EC. DAOS is a multi-version object store, so all the writes are non-destructive, right? So each time user writes something, DAOS will not overwrite the old version, old data version. Instead, it just stores the new version and put a timestamp on it. When user writes to an EC object, if the write is stripe size aligned, then the client can encode the data and send both the data and parity to servers. However, if the write is not stripe size aligned and it's a partial overwrite to the old data, then parity computation on the client is going to be very complex and expensive because the client has to read part of the stripe first, then compute parity based on merged data and send both the data and parity back to the server. And so if there is an application is pending data all the time, then it will kill the performance. So that's the reason DAOS does not do that. DAOS chooses a different approach for misaligned data or partial overwrite. DAOS client does not encode at all. Instead, it will replicate data and send it to the parity target. In this way, there is no read before write before the write. So, and the price of doing this is it will consume more space for misaligned data or partial overwrites. And to resolve this issue, the space reclaim service, aggregation, it is always running on servers, and it will. What it can do for EC is if the application wrote a bunch of misaligned data, it can encode data in the background and store parity, then free the replicated data. And this diagram shows how DAOS stores a partial over an object with partial overrides for EC4 plus 2, and we can see those partial overrides are replicated on the parity shard. EC is developed for data protection, so when there is a failure, node failure, then DAOS client can run in the degraded mode and reconstruct data in flight for application. And so for EC, we can say that there are two different failures. The first one is parity target failure. In this case, for read, an object lost a parity shard, and the second is data target failure. So the EC object actually lost a piece of data, although it's still recoverable from the parity. When we say the degraded mode, we only discuss about data target failure because losing a parity shard has no impact on read. So if we failed to read one of the data shards, the DAOS client should send RPC to the parity target. The parity target should return the parity and the timestamp of the parity. So the client can use this timestamp to request the data with this timestamp from all the data targets and reconstruct a missing piece of data based on those data and parity. Degraded mode read is the data recovery from the perspective of the client, and it's ephemeral because recovered data won't be stored back to the server. So, so the self-healing system and a rebuild protocol running on servers are the components that can actually recover data redundancy and store the recovered data persistently. So EC rebuild has no significant difference between with the replication rebuild. If we see it from the high level, I mean, from the implementation detail, there are always some difference, but from high level, they're very similar. And it is also similar with all the data migration use cases like we have introduced online server edition and Zhen. Each target should run the placement algorithm to detect objects impacted by the failure, then send OIDs to the fallback targets so they can reconstruct data or parity for those objects. And I think many of you know about the how DAOS aggregation works. The essential of aggregation is it will merge adjacent or overlapped extents to larger extent, then write it back. So we can reduce the fragmentation in SSD and the reduce size of index tree. But for EC, it's a little bit different. First, the simplest case is if a stripe is filled by many small writes, and as we have already introduced, these small writes will be replicated on the parity target. Now, if they already consist of full stripe, then DAOS can just merge them, compute the parity, and write the parity, then delete all those replicated data writes. And this part is straightforward. However, things can be more complex if the application submitted a bunch of partial overrides, then they never consist of a full stripe. And if there is old version of the stripe and the old version is encoded already, then the aggregation service, which runs on parity target, has to communicate with all the data targets to complete the aggregation. It should read the missing pieces from data targets and merge with the local replicated data, then encode and write the parity, then delete all the local replicated data. And this diagram is an example of EC aggregation for an object with some partial overrides. Yeah, again, that's probably all the content and I can present today about EC, and it's going to be available. I mean, the preview version is going to be available in the next release. After introduction of data protection and self-healing, we all understand DAOS IO request can be delivered to multiple object shards stored on different storage nodes, right? So automaticity of these distributed writes should be guaranteed. Otherwise, reads from different servers can be inconsistent and data is unrecoverable on failure. As we can see in this diagram, DAOS distributed I/O for data protection is a primary slave model. The primary server forward client request to slave servers, and this model can perfectly match with two-phase commit protocol. And this is exactly the reason that we choose two-phase commit as our distributed transaction protocol. In our I/O model, the primary server can be the transaction coordinator, whereas the slave server can be the transaction participant. The other reason that we need distributed transaction is initial DAOS API can only support upsert or merge, which means that either update the value of a key if the key is already there, or insert the key and value pair if it's not there. However, while trying to support different middlewares, we realized that we should support conditional operations. For condition update, we can we can run in insert mode and update mode, and they will fail if there is a conflict like insert key which is already existent or update key which is not existent. So distributed transaction is very important for supporting conditional update, because otherwise, for example, different replicas can get different execution results if there is a race. And if there is no transaction support, replicas can end up with inconsistent status. And now we can, because we implement our two-phase commit-based distributed transaction, so we can support this conditional operation already. And this is the last page, and it includes quite a bit of information, but we don't have enough time, so let's go through it quickly. The distributed transaction introduced in previous page is invisible to DAOS user. It only guarantee atomicity of internal distributed I/O of DAOS. But some applications or middlewares also have requirement of atomicity of a set of I/O operations. One well-known example is rename, right? So we extended our transaction protocol and exported through API. So user can explicitly start a transaction and put a bunch of fetch, update, punch operations within the transaction, then commit. These operations should either be all executed or all abandoned. Because DAOS client is a library, and DAOS does not monitor aliveness status of client. So if the client is silently dead, then it will leave a dangling transaction forever. To resolve this issue, DAOS actually cache all updates within the transaction and on the client, and pack them in a compounder RPC and send it out only on commit, API commit. The compounder RPC will be sent to a transaction leader, which is the actual two-phase commit protocol coordinator. It will unpack the compounder RPC and the forward RPC and drive the two-phase commit protocol status change for all involved servers. Because we have health monitoring protocol which can detect server failure, so we don't need to worry about the silent death and dangling transaction anymore in this model. And multi-version concurrency control MVCC rules ensure the distributed transaction execute as if they are serialized in their time order, and they're implemented in our versional object store walls. And yeah, we don't have time to go through those rules. So if you are interested in the details, please check the document in the source tree. Okay, yeah, that's all the new features.
Thanks a lot. Thanks a lot, Liang.